Hello there, welcome to the 8th session of the Introductory Biostatistics Distance Learning course. In the previous session, we talked about an introduction to hypothesis testing. In particular, we looked at the one-sample t-test. We said that we use the one-sample t-test when we're comparing the mean of a continuous variable to a particular number. But you might think this isn't really that commonly done in practice, because when are we going to compare to a particular number? Instead, what's more likely is that we're going to do a two-sample t-test. So this comes up all the time in medical research. For example, in a clinical trial where you're comparing a treatment with a placebo, so that's a two-sample t-test, or in observational studies where you compare the exposed versus the unexposed. So two-sample t-tests are much more commonly seen in practice than one-sample test where you compare the mean of a group to a particular number. So we're going to continue with these examples from multiple sclerosis. So there are two main types of MS. One is relapsing and one is progressive. And so we want to know, is the immune system involvement different in the two forms of MS? So this is a two-sample setting. We have relapsing MS and progressive MS, and we want to compare this marker for the immune system with these two different groups, the relapsing and the progressive. Okay? So the outcome in this case, the outcome variable in this example, is a measure called CD26, which is a continuous variable. Okay? You always want to think about the type of variable you're dealing with, because that will guide the type of statistical tests that you want to use. So far, we've only talked about tests for continuous variables, but as we move forward, we'll cover other types of tests. Okay, so the outcome is this CD26 measure of the immune system, a continuous variable, and now we have an explanatory variable. And that is the group membership. Okay? So remember, we said we have two groups. Group membership. Particular, relapsing versus progressive. Okay. So how would we answer this question of whether these two groups, relapsing and progressive, vary on this continuous outcome of interest? Well, we'd collect a sample from each group. Okay? Then we would measure the mean that we got in each group. So I'm just going to clear this. And suppose the mean in the relapsing patients, the relapsing mean, is equal to 37.4. And suppose the progressive mean is equal to 44.3. Okay? So these numbers are different, and of course they'll be different every time. We're never going to get exactly the same numbers in two groups. But what we want to know is the difference between them more than just chance. Is there a real difference between the two groups? Okay? Is it statistically significant or clinically meaningful? Okay? So in order to answer that question, remember a great way to start off when you're looking at data is to produce plots or graphs, because it really helps you visualize the difference between groups. So let's look at a histogram for this experiment. Okay, here it is. So you can see that there were two experiments conducted here. Means in the two groups are the same in both experiments. Okay? In particular, you can see the progressive group is here. Whoops, sorry about that. The progressive group is here and here. and their mean is the same in both experiments. Actually, here we can see the median, right? Remember, a box plot gives us the median, which is there and here, and the median for the relapsing group is here and here, the median, okay? But you can see what's different in the two experiments. So the medians are all the same, but the amount of variability is much different in the two experiments. Experiment 1 appears to have much less variability than experiment 2. Okay, so how would we set up, keep this picture in mind. Same medians and presumably same means, but very different variability. Much less variability in experiment 1 over here as opposed to experiment 2 where there's lots of variability. Okay? All right, so let's go through our 7 steps of hypothesis testing, just like we did before. Remember, step 1 is to write the null hypothesis. And so here, the null hypothesis would be that the mean, I'm just going to write R for relapsing, is equal to the mean in the progressive group. Okay? Another way of writing that same thing, another way of writing that same thing would have been that same null hypothesis, is that the mean in group R, the relapsing, minus the mean in the progressive group is equal to 0. That's another way of saying they're equal. And so now the alternative hypothesis, I would write the mean in the relapsing group minus the mean in the progressive group is not equal to 0. Okay? And so what kind of data am I dealing with? Well, my outcome, we said, was continuous. Again, as we move forward in this course, you always want to think about the types of variables that you're dealing with. So here we have a continuous outcome, and our explanatory variable is group membership, and that's binary, right? Because you're either in the relapsing group or you're in the progressive group. So what test can we use to compare a continuous outcome with a dichotomous or binary explanatory variable? Well, it's the two-sample t-test. Okay? So the two-sample t-test. Okay. Remember, we said that every statistical test has underlying assumptions that need to be met in order for you to use that test. So what are the assumptions of a two-sample t-test? That the underlying population distribution for this CD26 is normal. And that's usually met for most continuous variables, that assumption. And also that we have independent observations. Okay, so that is to say, my CD26 value isn't going to impact yours. Okay, and so then to calculate a p-value, we need to understand if the difference in the means is large relative to the variability in the data. So think back to the histogram that we showed with the two experiments. What we're trying to do is understand if the difference in means is large relative to the variability in the data. So in that histogram, the means were the same in the two experiments, but the amount of variability was much different. And then we'll use a statistical software package such as Stata to get a p-value. Okay? All right. So what does the test statistic look like? So the basic form of a test statistic is, as we saw before for the one sample case, now we're just extending it to two samples. So we're going to take x bar 1, the mean in the first group, minus x bar 2, the mean in the second group, minus their population means, okay, and then divide by an estimate of the variability, the standard deviation. So the sample standard deviation for x bar 1 minus x bar 2. Okay? Is the observed, so the question we're asking is the observed mean difference similar to the hypothesized mean difference? Okay, so is the observed mean difference, which is this piece, similar to the hypothesized mean difference, that's this piece, relative to the variability in the data? The variability is captured by this standard deviation in the denominator. Okay, so is the observed mean difference similar to the hypothesized mean difference relative to the variability in the data? Okay, all right. So sometimes we're going to assume that the variance in the two groups is equal. Okay, so we would write that as follows, that sigma 1 squared equals sigma 2 squared, and since that they're equal, I don't need those subscripts, I can just write they're equal to sigma squared. Okay, so this is an assumption about the population variance. Okay, so we never know the population variance, but this is an assumption that we sometimes want to make in a two-sample t-test. Okay, so again, we're not going to know the population variance, so instead we're going to estimate it with the sample variance, right? S squared. So S squared sub 1, S squared sub 2, and so on. Okay? And since we have two estimates of one quantity, we can pool the estimates. Okay? So this is in the situation where we want to assume equal variances. And we're going to talk a little bit later about relaxing that assumption to not assume equal variances, but for now we're going to start off with that assumption. And so we have two estimates of the quantity. We have the variance in group 1, and we also have the variance in group 2. So we're going to take them and pool them together to get one estimate. Okay? All right. Okay, so let me pull. So this was our test statistic, remember? All right, so this is a formula for the pooled variance, okay? So that's what this P is for, it's pooled. Remember, we have the estimate from the first group and the second group. We're going to pool them together, and S squared, again, is our sample variance, okay? So how do we calculate that? We take the number in the first group, subtract 1, multiply by the variance in the first group, number in the second group, subtract 1, times the variance in the second group, divide by the total sample minus 2, okay? So you can see why we do this, because if the number that we have in group 1, N1, is much different from the number we have in N2, well, we want to weight those accordingly, okay? So this is just, this pooled estimate you can think of as a weighted average, right? We want to weight the sample variance from the group that has the larger sample size, okay? All right, and so that gives us this pooled estimate of the variance, which we write S squared P. Okay, and then so now that we have that, we can construct a test statistic based on the pooled variance, which looks like so. Okay, so just like we saw before, the sample estimates minus the hypothesized values divided by the pooled variance, right? Okay, let me delete all this stuff so that the formula looks okay. Okay. All right, and this test statistic has a t-distribution. Remember, we use t-distributions in cases where, in basically all cases where we don't know the population standard deviation, and so we use the sample standard deviation. Remember, again, the distinction is always between the sample estimate and the population, and the sample estimates are written with normal letters, where the population quantities are written with Greek letters. Okay. And so this test statistic has a t-distribution with n1, which is the number in the first group, plus n2, which is the number of patients in the second group, minus 2. Okay, so that's the degrees of freedom. Remember, we said that different distributions have different parameters. And we said that, for example, the normal distribution, the parameters were the mean and standard deviation. For the t-distribution, the important parameter is the degrees of freedom. Okay? And so here we have n1 plus n2 minus 2 degrees of freedom for this test. Okay? So again, that's the case where we're willing to assume equal variances. What if instead we look at our data and it doesn't look like the variances in the two groups are equal? And we're not willing to assume that they are equal, so we have to work with unequal variances, okay? So what would our test statistic look like in the case of unequal variances? It would look like this, okay? So you can see same numerator as before, sample quantities minus hypothesized values divided by measure of variability, but this time instead of having S sub p for the pooled estimate, we have the estimate from group 1 and the estimate from group 2. Okay, so again, don't worry about the particulars of the formula, just that you understand the way it's constructed and what it's doing. You take your sample estimate minus the hypothesized value, divide by whatever estimate of variance you want to use. Here we're not using the pooled estimate. We think that the groups have unequal variances, and so we don't pool them together, we keep them separated. Okay? So the unfortunate thing about this unequal variances test statistic is that the distribution of it is difficult to derive, and therefore we have to approximate it using a t-distribution with this strange formula for the degrees of freedom. Let me show you that. That's this thing. So you can see it has this kind of, I forget which Greek letter this is, this thing that looks like a V. But this has V degrees of freedom, which are defined by this. So you can see it looks pretty complicated. But again, don't worry about it because the statistical software package will always take care of this for us. Okay? This is called the Satterthwaite approximation. I don't know how exactly to pronounce that, so let me write it down. It's the Satterthwaite. Whoops, Satterthwaite. That's somebody's last name. He came up with this. So, okay. So when you complete a two-sample t-test in Stata, we'll see that in the next session. The variances are not assumed equal, then this Satterthwaite approximation is used. Okay. And remember what we said about the degrees of freedom for a t-test. Let's pull up the picture. We said that as the degrees of freedom increase, which means as your sample size increases, the shape becomes more and more like a normal. So if you look here, the blue line, that's the normal here, normal. It's the one that's on top here and on the bottom here. This means it has, the normal has short tails, right? Because it's at the bottom here and then at the top there. So you can see a t-distribution with 1 degree of freedom, which is this one, the red color, that refers to this curve. So you can see it has very long tails over here. It's the red one which is on top. But as the degrees of freedom increase to 5 with the green, then to 10 with the orange, and to 100, these become more and more like the blue curve, which is the the normal curve. Okay? All right. So I don't really... Oh, okay. I know why. I was thinking I don't see this 100, and the reason is the 100 one almost coincides with the normal curve. Okay? So you can see the red is the 1 degree of freedom t distribution. The green is the 5 degrees of freedom. The orange is the 10 degrees of freedom, and we keep getting closer and closer to this blue line. And then the one with 100 actually coincides with the normal. Okay. All right, so let's go back to our 7 steps of hypothesis testing. Remember, we had said that the null was that the mean in the relapsing group is equal to the mean in the progressive group. And remember, in my hypothesis, in my null and alternative hypotheses, I always write the population parameter. That's why I use these Greek letters, right? We're interested in doing tests about the population parameters. We have the sample parameters, x bar for relapsing and x bar for progressive. We're not interested in whether those are different, right? Because, yeah, they're different. They're always going to be different because of our sampling variability. Our tests that we want to do, we want to involve the population parameters, which is why I wrote the null hypothesis using the Greek letters, because we're interested in the population parameters. Okay, so the alternative hypothesis is going to be that they're not equal. What kind of data are we dealing with? We have a continuous outcome. A binary explanatory variable, or dichotomous, 2 groups, binary explanatory. Okay, what kind of test are we going to do? We said we're going to do a 2-sample t-test. Okay, then we get our sample quantities from our data set, and it turns out that x bar in the relapsing group is 37.4, and x bar in the progressive group is 44.3. So they're different, but I don't know yet if they're statistically significantly different relative to their variability. So now I need a p-value, that's step 5. And that I would get from my statistical software package. We'll work through an example in the next session. Turns out in this case it's 0.028. Now I have to make a decision based on this p-value. Well, since the p-value is greater than 0.05, it's 0.28. Since it's greater than 0.05, we fail to reject the null. Fail to reject. Remember, we always fail to reject. We don't accept the null. We fail to reject it because the p-value is greater than 0.05. And then we write our conclusion. We say that the mean difference in CD26 between the group relapsing and progressive is not statistically significant. Okay? All right, good. So those are the 7 steps, and again, we'll work through an example. Now let's just look at what it looks like in the output from Stata. Okay, so here's our output. We would use the command ttest. The variable is called expression, so that's going to change each time. Ttest we'll type in each time, obviously, but the variable that we're working with will change. Here the variable is called expression for that CD26. By group, right? Group membership tells you about progressive versus group is the variable in this data set that tells you whether you're in the relapsing or the progressive group. And then unequal says, hey, use unequal variances. Okay. Here are our summary statistics. The means in the progressive and the relapsing groups. Okay. Then we get group-specific 95% confidence intervals over here. And remember that duality that we talked about between confidence intervals and hypothesis testing. Namely, these confidence intervals overlap, right? Because for the progressive, it looks like the confidence interval goes from 32.3 to 56.2. And for the relapsing, it goes from 32.4 to 42.4. So these confidence intervals definitely overlap. So from there, I already know that I'm not going to reject my null hypothesis. Because the confidence intervals overlap, the groups are not significantly different, and I'm going to fail to reject my null. I can already tell that looking only at the confidence interval. Okay. Similarly, you'll see that Stata gives you a 95% confidence interval for the difference. And that gives you the same information because since the confidence interval for the difference contains the number 0, right? 0 means no difference. So since the confidence interval contains 0, I'm going to conclude that there's no significant difference between the groups. I fail to reject. So you can see multiple ways that you would arrive at that same conclusion. And here's our two-sided p-value, 0.27. Remember, this is saying the alternative, this piece is saying the alternative is that the difference between the two groups is not equal to, the exclamation equal means not equal. And the corresponding p-value is 0.275. That's greater than 0.05. So we fail to reject. Okay, and then here's our one-sided p-value over here. But again, we're going to be doing two-sided tests almost always. Okay, so again, let's go back to those different experiments that we were talking about. Remember this? So there's a significant difference in experiment 1, it turns out. So if we were to do this, a two-sample t-test here in experiment 1, we would get a p-value less than 0.001. So that's a significant difference. And here, that was the example that we worked through. The p-value was 0.28. Okay? So what does this tell us, right? It tells us that it's not just the means or the medians. Whoops. It's not just the means or the medians, because the medians in the two groups were exactly the same. Hypothesis testing in these conclusions also incorporate the amount of variability. So there was much more variability in experiment 1 than there was in experiment 2. Okay? All right, and so we already talked about that another way to investigate our hypothesis of a difference in the means between the two groups is to use the confidence interval. Okay? And so we said that the confidence interval for the difference contained the number 0, and therefore we knew that there was no significant difference between the groups. Okay? So to summarize, when we want to compare the mean of a continuous outcome, again, always think about the kind of data you're working with. The mean of a continuous outcome between two groups, we use a two-sample t-test. And to determine if the groups are significantly different, we calculate a p-value, or analogously, we can use the 95% confidence interval. Okay? So let's talk a little bit more about the assumptions. We said every statistical test is going to have assumptions. So there was the equal versus unequal variances. So it's probably better to generally use unequal variances. You might wonder, why on earth would you ever use equal variances? Well, if you use equal variances, your test has more power. And by power, we mean you're going to get, the likelihood that you're going to get a significant p-value is greater, right? Because you're making a leap of faith that the groups have equal variance, so that gives you more information. You're assuming more, and therefore you're more likely to come out at a significant difference. So, but in general, it's better to start with an unequal variance assumption and then take a look at the data and see what you think, okay? We can also test. What's interesting now is, remember, so far we've done hypothesis tests that only involve the mean. Remember, we said something like the null was that the mean in the relapsing was equal to the mean in the progressive. We can also do a test for the variances. So we could say the null is that the variance in group 1 is equal to the variance in group 2. And obviously the alternative would be that they're not equal. Okay? So here, in this case, in this test for equal variances down here, rejecting the null hypothesis in this case would mean we're rejecting the null that they are equal and saying that it looks more likely that they're not equal, okay? Failing to reject in this case means that the assumption of equal variances seems reasonable, okay? So what does the data output for this look like? The test of equal variances. Let's take a look at that. Okay, so you can see it's a test for the standard deviations or variances. Same thing. One's just the square root of the other, right? The standard deviation is the square root of the variance. So this says standard deviation test. Expression is the name of the variable in our data set. By group, group is the variable in the data set which indicates whether you're in progressive or relapsing. And then here's our p-value. P-value is 0.07, or sorry, 0.02, okay, which is less than 0.05. So we reject the null. Reject null. Remember, the null was that the variances are equal. So we reject the assumption, the null that the variances are equal, and say that we have to use unequal variances, okay? So that was one assumption, that of equal versus unequal variances, we can do a test and so on. Then we said that the underlying populations that these things come from have to be normal, okay? So what if this assumption isn't true? It turns out that the t-test is what statisticians call robust. If a test is robust to departures from this assumption, then that means even if this assumption doesn't hold, your test is likely to be valid. So that's good news. It's a really good quality of a test for it to be robust to departures from assumptions, okay? So the t-test is very robust to departures from this assumption for reasonable sample sizes. That's the caveat, for reasonable sample sizes. And you might say, what do you mean by a reasonable sample size? Let's say n greater than or equal to 50. something like that. Any number, any one number that you choose is going to be arbitrary, so don't get hung up on this n of 50. But just know that as the sample size increases, departures from the assumption of normality are going to be less of a big deal for the t-test, okay? But in any case, how would we assess this normality assumption? Well, we can plot the data, see if it looks normal. We can do a formal statistical test. Okay, or we can use so yeah, those are usually the available options. Okay, so we can kind of do it informally through a plot, or we can do it formally through a statistical test. Okay, and you can remember we did a formal statistical test for the equal versus unequal variances and so on, but plots are often way more informative. So what would a plot look like? So you would just take your data, perhaps come up with a histogram. So we need to look at each group separately, right? We have two groups, but this looks pretty darn normal. Usually you want to put the onus on it looking skewed, if that makes sense. You know, you don't want to be too strict about whether it looks perfectly normal or not. I would say this looks pretty darn good, actually. Okay? So this is for one of the groups. You would have to do the other group as well. Okay. What's another plot we can look at? This is called a QQ plot. So if the data are perfectly normal, they fall on this line here. And for the most part, it looks like the data do fall on that line, with the possible exceptions on the tails. But again, we're saying that we're looking for egregious departures from these assumptions. Okay? So those are the graphical approaches. We could also do tests for normality, formal statistical tests. So there's one called the Shapiro-Wilks. And so let's take a look at what that looks like in Stata. So the command is swilk. Here's the variable that we're testing the normality of. It gives us a p-value. Here it's greater than 0.05, so we would fail to reject, right? Or we can do a... So the null here is that it is normal, right? The data is normal. So here, since we got a p-value greater than 0.05, we fail to reject and conclude that this assumption of normality seems reasonable. Okay, we can also do a skewness kurtosis. Skewness and kurtosis are these measures of whether you have a skewed distribution, as the name implies. So what does that look like in Stata? Here's that one. Okay, same thing. So now here's the command, sk-test. Here's the variable, same as before. Here's a p-value, again greater than 0.05. So normality seems okay. Okay. So what do we do? In both of these cases, we failed to reject and we concluded that normality seems reasonable. What if normality doesn't hold? We do one of these tests, or we look at one of those plots, and the thing is not looking normal. Well, what are our options then? We can transform the data. What do we mean by that? We don't mean we change the data, that would be funny, to make it normal. But instead, we can do for example, a log transformation. and the data might then be normal on the log scale, and then we can conduct our statistical test on the log scale, okay? Or, if that doesn't appease us, we can move to what we call a non-parametric test, okay? So what does this mean? So a t-test is a parametric test, okay? So t-test is parametric. What does that mean? Well, since we have this normality assumption, when we assume a distribution, like we assume normality for a t-test, that's called a parametric test. A non-parametric test doesn't make those normality assumptions, okay? And so the analog, the non-parametric analog for a two-sample t-test, so the non-parametric version of a two-sample t-test is called the Wilcoxon rank sum. And we're going to talk more about we'll have a whole lecture devoted to non-parametric tests. This is just to give you the background, okay? So t-tests, they're more powerful. That means you're more likely to be able to detect a difference between groups when there is one. But if normality, the assumption of normality doesn't hold, and transforming the data doesn't seem to work out for you to give you normal data, then you can move on to a non-parametric test, which is, again, less powerful to detect differences, but it doesn't make that normality assumption. So that is called a Wilcoxon rank sum test. Okay? And again, we'll talk more about this in a future session. Okay? Okay, so the t-test is, we said that it's quite robust to departures from normality, especially with larger sample sizes or moderate sample sizes. And so if we have a very small sample size, we might pursue methods that do not require normality assumptions. These are called non-parametric tests. Okay? All right. So I'm going to put up this next thing that I'm going to put up is a very, very helpful way of thinking about this whole class, everything that we're learning here. Okay? So we've mentioned several times that it is extremely important to always know the type of data that you're working with, okay? So if you think in terms of this kind of matrix that I put up here, you're going to have a very, very good understanding of what's going on in this class, okay? So you want to always think, what type of outcome variable do I have? Is it continuous? Is it ordinal? Is it dichotomous or binary? Is it a time to event variable? So that's the outcome. And then what kind of explanatory variable do I have? And then once you have decided those two things, you'll be able to determine the type of statistical test or analysis that you need to conduct. Okay? So always think in terms of this matrix. So far, we've only done the first row, what's highlighted in orange. That's all we've covered so far, but we'll cover all the rest of these as we go through the course. Okay? So all we've talked about is if you have a continuous outcome and a dichotomous explanatory variable. What do we mean by that? Well, we looked at some continuous measure of the immune system. It was a continuous variable. And the explanatory variable was the progressive group versus the relapsing group. So that's why we have this dichotomous or binary explanatory variable. Were you in the progressive group or the relapsing group? And then if this is the case, we want to use a t-test. Okay, so always think of in terms of this matrix, and you can see how we're going to build up. Next, we'll think about a continuous outcome with a categorical explanatory variable, and then a continuous outcome with a continuous variable, and so on. And then we'll deal with different types of outcome variables. Okay, so I'll stop there, and I will see you in the next session.